Today on AI Paperslop, we are diving straight into vision pre-training for dense spatial perception. It's a new paper by researchers at Ant Group and Raviant.
Yeah, and it is a really fundamental departure from the standard pre-training playbook we are used to.
Exactly. I mean, if you are an ML engineer or, a researcher building visual foundation models for embodied AI, robotics, anything requiring a native understanding of 3D space, this architecture is just a massive shift.
Right, because historically, boundaries and edges, they've been treated as these fragile downstream features.
Yeah, like you try to carefully extract them at the very end of a vision pipeline using fine-tuning. But the core insight here is that the field needs to stop treating geometric boundaries as downstream outputs.
They need to be the foundational self-supervised learning signal from, the very first epoch.
Totally. So this paper introduces a self-supervised pre-training paradigm called masked boundary modeling. Basically, it forces a vision transformer to reconstruct subpixel boundary tokens from day one.
And by discretizing these continuous boundary fields into a categorical classification problem, the researchers successfully trained LingBot-Vision.
Which is wild, because it's a 1 billion parameter model that explicitly beats the 7 billion parameter Dino V3 on dense spatial tasks, specifically depth estimation.
Yeah, outperforming a model 7 times its size is no joke.
Right. So today in this deep dive, we are breaking down the architecture, the math behind bootstrapping geometry from absolute scratch, and how this methodology finally solves the semantic spatial trade-off.
I think to really understand why LingBot-Vision is crushing these dense benchmarks, we have to look at the inherent flaw in how standard visual foundation models are pre-trained today.
Yeah, so we have these ubiquitous models, right? Like CLAP or the standard Dino iterations. And these architectures are obsessively designed around semantic invariance.
Right, which is the bedrock of categorization. Like if you want a neural network to identify a chair, you want the internal representation to be invariant to the environment.
You want it to know it's a chair, whether it's upside down or, half hidden behind a desk or in a really dark room.
Exactly. The network is actively encouraged by its loss function to just discard the exact geometric details of the scene. It isolates the abstract concept of chairness.
Chairness, right. But that exact geometry, like the precise depth discontinuities and the actual physical boundaries of the object, that is the exact data required for physical intelligence.
Yeah, if you were programming a robotic arm to grasp that chair, an abstract semantic token of chairness is completely useless.
It's going to grab thin air. The system needs to calculate precisely where the edge of the armrest terminates in 3D space.
Right, so these semantic models excel at recognizing what an object is, but they fail pretty hard at dense spatial structure.
And that failure stems directly from the dominant pre-training methodology, which is masked image modeling.
Yeah, frameworks like masked autoencoders or MAE and IBOT, they rely heavily on random masking.
Which means you take an input image, chop it into patches, and randomly mask out a huge chunk of those patches, sometimes up to 75%.
And then you just force the student network to reconstruct the missing data.
Right. But the critical flaw there is that random masking is content agnostic.
Yeah, the algorithm has literally no awareness of the structural topology of the image it's masking.
I always look at standard random masking, like trying to learn a language by randomly blanking out letters in a book.
Oh, that's a good way to frame it.
Right. Because it treats a crucial action-driving verb exactly the same as just a random comma.
Exactly. If the algorithm randomly drops a patch in the middle of a blank, flat, white wall, the network can easily minimize this reconstruction loss.
It just looks at the neighboring white patches and copies the pixel values. Easy.
But if the algorithm drops a patch that contains the complex geometric edge of a table, that is a massive structural verb.
Yeah, and if the goal for the model is spatial understanding, the network should be forced to focus its compute on those structural verbs rather than the redundant commas.
Right, because when the network is allowed to minimize loss by filling in flat spaces, you are basically wasting model capacity on regions with almost zero irreducible structural information.
A patch straddling a physical boundary is like the most information-dense region of the image.
Exactly. The network cannot just interpolate the pixels next to it. To reconstruct an edge or a corner accurately, the model actually has to develop an internal representation of the scene's geometry.
So if random content-agnostic masking is the bottleneck, the logical next step is intelligent masking. The architecture needs to actively decide which patches to hide.
But the challenge there is how to achieve that without relying on expensive human annotations.
Oh yeah, human labeling for dense subpixel boundaries is incredibly tedious.
And completely unscalable for foundation model pre-training. You just can't do it.
So the authors solve this by introducing what they call boundary-forcing masked modeling.
Right. Instead of relying on a random number generator, the model itself dynamically identifies which patches contain significant boundaries during the forward pass.
And once it locates those boundary-bearing patches, it intentionally forces those specific tokens into the student network's masked set.
Which is brilliant because you guarantee that the student network is forced to reconstruct the hardest, most geometrically complex parts of the image in every single batch.
But the boundary tokens aren't just forced into the mask, right? They are given a dual supervision target.
Yeah, this is key. In a standard setup like IBIOT, a masked token gets a purely semantic target. The student tries to match the abstract feature representation generated by the teacher network.
But semantic targets are inherently ambiguous at the exact pixel where two regions meet.
Exactly. Like, is a pixel on the very edge of a dog classified as dog, or is it classified as the grass behind it?
The semantic boundary is blurry by definition.
Right. So in this boundary forcing setup, the boundary tokens still receive the standard semantic objective to preserve their categorization abilities, but they also receive a specific explicit geometric target.
The student has to actually reconstruct the dense boundary field itself.
Yeah.
But hang on, stuck on a paradox here. And if you're listening, you might be thinking this too. The model is training entirely from scratch using self-supervision.
Right.
If the teacher network hasn't learned any geometry yet, because we are at like epoch 0, how does it know where the boundaries are in order to mask them and generate targets?
Yeah, it's a massive chicken and egg problem.
Because you're saying the teacher masks the boundaries so the student can learn them, but the teacher shouldn't be able to see the boundaries in the first place.
Exactly. The very tokens you most want to mask are the ones the network cannot yet reliably locate because its weights are randomly initialized.
So how do they fix it?
It's the central architectural hurdle of the paper. They solve it by using an elegant mathematical trick to bootstrap boundaries from absolute scratch, which they call finding one.
Okay, let's unpack finding one.
Well, to understand it, we have to look at how they represent boundaries. They do not use a standard binary edge map where a pixel is just a 1 or a 0 edge or not edge.
Right. They use a dense, highly over-parameterized representation called a boundary field. Let's visualize that boundary field for a second.
Yeah, imagine a single straight line segment in an image, like the edge of a door frame.
Okay. In a binary map, only the pixels exactly on that line contain information.
But in this boundary field, every single pixel within a wide radius surrounding that line segment stores a dense vector of information about the line.
So a pixel, say, 5 pixels away from the door frame, stores its exact distance to the line.
The angle pointing toward the nearest point on the line and the angles pointing to the two endpoints of the segment.
That is massively redundant.
It is incredibly redundant. Any single pixel in that surrounding support region carries enough geometric data to decode and reconstruct the entire line segment.
And for finding one, the authors leverage this exact redundancy. Because when the teacher network is untrained, these boundary field values are effectively just random noise.
Right. The network is outputting arbitrary distances and angles. It's just spitting out geometric garbage at that stage.
But then they apply a lightweight, frozen corner point detector.
Yes. Corner points like intersections of sharp gradients are computationally cheap and really reliable to extract, even without learned weights.
So the system fixes those detected corner points in place.
And then it allows all the nearby pixels with their noisy random vectors to essentially vote on where the line segment connecting those corners should be.
So because of the massive redundancy in the boundary field, the random noise just cancels out during the vote aggregation.
Exactly. The system can decode structurally plausible line segments right from the very first training step, simply by taking a consensus of the noise anchored between two fixed corners.
So the redundancy basically acts as a built-in error correction protocol.
Yeah. The newborn teacher network can pull usable geometric targets out of the image just by anchoring to corners and aggregating the random vectors.
But I imagine you can't just feed those bootstrapped lines directly to the student network. Like, what if the image features a highly textured carpet?
Right. The network is going to detect chaotic gradients, drop a bunch of corner points, and vote on line segments that aren't actual structural boundaries.
It's just hallucinating edges in the fuzz.
Yeah.
And feeding hallucinated structure back into the training loop is a fast track to feature collapse.
Exactly. The teacher network has to clean up these noisy bootstrapped lines before passing them as targets.
And they accomplish this using a contrario validation, right?
Yes, which is a classical statistical test derived from detection theory.
Wait, how does a statistical test actually filter out the carpet texture while keeping the physical geometry?
So the test operates by establishing a null hypothesis. In this case, the null hypothesis is a uniform distribution of orientations.
Meaning it assumes the pixel gradients in the image are just pure random chaos.
Right, and when the vote aggregation proposes a line segment, the a contrario test analyzes the alignment of the pixels along that proposed line.
Okay.
And it calculates the probability that this specific alignment occurred purely by chance under that null hypothesis of random chaos.
So if the proposed line is drawn across that textured carpet, the pixel orientations along that line are going to be pointing in 100 different directions.
Exactly. The statistical test looks at that and determines there is a very high probability this chaotic alignment occurred by chance.
So it fails to reject the null hypothesis and deletes the hallucinated line.
Yep. Conversely, if the proposed line traces the sharp, consistent edge of a doorway, the pixel orientations will be uniformly aligned.
And the test calculates that the probability of such strong alignment occurring by random chance is astronomically low.
Right. It rejects the null hypothesis and validates the line segment as a genuine structural boundary. And this filtering process requires absolutely no learned parameters.
It is purely mathematical. So just to recap the loop, the teacher network generates the noisy field, anchors it to the corner points, aggregates the pixel votes to form lines,
runs the a contrario statistical test to delete the hallucinations,
and finally feeds those validated boundaries to the student as targets.
Exactly. And those targets are fed back via exponential moving average updates, or EMA. By updating the teacher network slowly as an average of the students' weights, the system stays stable while the geometric representations iteratively improve.
Okay, so the bootstrapping mechanism completely solves the initialization problem. But when the student network attempts to actually learn from these validated boundaries, we hit a pretty severe mathematical wall.
Yeah, we run into the notorious issue of how self-supervised learning handles continuous variables.
Because the boundary field vectors we discussed, the distances and the angles, those are continuous floating point values.
Right, and in self-supervised teacher-student architectures, attempting to get the student to directly regress continuous vectors almost always leads to regression collapse.
The student network quickly learns that the safest, laziest way to minimize its loss function is just to predict the mean value for every single pixel.
Exactly, which results in a completely flat, constant output that contains no features whatsoever.
So the core architectural innovation of this paper is how they bypass that regression collapse entirely. They introduce the categorical reparameterization of boundary fields.
Which sounds complicated, but it's brilliant. Instead of forcing the network to output a continuous regression variable like trying to predict that the distance to a line is exactly 3.1415 pixels.
They discretize the entire continuous range into k separate categorical bins.
Right. They transform the dense boundary prediction task into a per-pixel classification problem.
And moving from continuous regression to categorical classification fundamentally changes the stability of the loss landscape.
It completely changes the game.
I like to think of it as the difference between a continuous tuning dial on an old analog radio and a multiple choice test.
Yes, that's exactly it.
With a continuous dial, the student network is constantly overcorrecting, trying to find the exact micromillimeter of the signal to minimize the continuous loss, which eventually degrades into static or collapse.
But by snapping the prediction space into k distinct bins, the network just has to classify the pixel into bin A, B, C, or D.
Right. And the reason this reparameterization is so critical is that the entire underlying machinery of modern self-supervised learning is already optimized for classification.
Not continuous regression. By framing the boundary objective as a categorical problem, the boundary branch of the network can instantly utilize the exact same stabilization mechanisms that semantic models use.
Specifically, it can leverage Sinkhorn-Knopp sharpening.
Yes.
For those dealing with mode collapse in their own architectures, Sinkhorn-Knopp is the matrix scaling algorithm used in frameworks like Dino to ensure the model doesn't get lazy.
Right. It forces a uniform marginal distribution across a batch.
Meaning the network can't cheat the loss function by assigning every single pixel to the exact same category.
And if the authors had kept the boundary field as a continuous regression problem, they could not have used Sinkhorn-Knopp.
They would have had to invent bespoke, untested regularization techniques to prevent the math from collapsing.
which is always a nightmare. By making it categorical, the boundary learning process basically inherits the battle-tested stability and scaling properties of modern semantic SSL.
The semantic representation and the geometric representation can finally co-emerge peacefully within the same transformer.
Instead of fighting each other for model capacity.
Okay, so we have intelligent boundary-forcing masking, a statistical bootstrapping mechanism to solve the zero-knowledge start, and categorical reparameterization to prevent regression collapse.
The theoretical foundation is incredibly solid.
But the empirical results are where this gets particularly relevant for actual deployment. The authors scaled this architecture up to build LingBot-Vision, which is a 1 billion parameter model utilizing a ViViTG, or giant-sized vision transformer, backbone.
And when evaluated on dense spatial tasks, LingBot-Vision demonstrates significant dominance.
Yeah, on the NYU Depth V2 benchmark, which is, a heavily utilized standard for depth estimation, LingBot-Vision achieves the highest accuracy across all evaluated models.
It explicitly outperforms DAV3.
Which operates with 7 billion parameters.
Right. LingBot-Vision achieves superior dense spatial perception with only 1 billion parameters.
It's vastly outperforming its parameter count because the fundamental pre-training paradigm forces it to natively understand 3D space rather than trying to infer geometry from semantic tokens after the fact.
And the efficiency scales down as well, which is crucial for distillation, because the ultimate goal of training these massive foundation models is usually to distill their feature representations into smaller, low-latency models.
Yeah, models that can actually be deployed on edge devices or robotic hardware. You cannot run a 7 billion parameter transformer in real time on a robotic dog's localized hardware without just unacceptable latency.
Exactly. And the dense geometric features generated by LingBot-Vision proved to be highly robust during the distillation process.
The researchers actually distilled the 1 billion parameter model down to a 0.3 billion parameter student model.
And that tiny, highly efficient student model matches the NYU Depth V2 accuracy of the 7 billion parameter Dano V3.
A 0.3 billion parameter model matching a 7 billion parameter model on dense depth estimation. That represents roughly a 23x reduction in parameter count without sacrificing accuracy on the benchmark.
For anyone actively deploying embodied AI, that kind of efficiency gain alters the hardware constraints of the entire project.
Totally. The authors also applied this initialization to their custom depth completion system, upgrading it to LingBot Depth 2.0.
Yeah, and by simply replacing their previous encoder initialization with LingBot-Vision, the system achieves state-of-the-art performance across 14 distinct depth completion benchmarks.
There is a specific graph in the paper detailing data scaling that really highlights why this pre-training methodology is so durable.
Right, because a common assumption in deep learning is that if you throw a massive amount of downstream fine-tuning data at a model, the sheer volume of data will eventually override and wash out any specific advantages gained during the pre-training initialization.
But the scaling graph directly contradicts that assumption for spatial tasks.
It does. The researchers scaled the downstream training data for the depth completion task from 3 million samples all the way up to 150 million samples.
And as the fine-tuning data volume grows, the performance curve for the Dino V2 initialization begins to saturate. It just flattens out.
Because the model lacks the native spatial priors to fully leverage the dense data.
Right. However, the performance curve for the LingBot-Vision initialization keeps improving monotonically.
The performance gap between the two models actually widens at the 150 million sample mark.
That compounding scaling behavior is the definitive proof of concept. The spatial native pre-training does not wash out at scale.
No, it acts as a permanent structural multiplier on all downstream fine-tuning data.
If the foundation model does not natively understand spatial geometry at the self-supervised pre-training level, no feasible amount of downstream data can fully compensate for that architectural blind spot.
It really forces a reevaluation of how the field constructs visual tokens. Boundaries are no longer just this artifact you hope the model learns implicitly.
They're a scalable pre-training principle that fundamentally bridges the gap between semantic pattern recognition and 3D physical reality.
Exactly.
So before we wrap up this deep dive, there is a broader implication of this reparameterization technique worth considering. The authors proved that geometric boundaries, which are a purely structural, continuous physical signal, can be seamlessly reparameterized into categorical bins.
Right, to teach a foundation model the rules of 3D space using standard classification machinery.
Exactly. So If the physical structure of an image can be successfully discretized into self-supervised tokens, what other fundamental physical properties could we apply this mathematical trick to?
That's a fascinating question.
Right. Could we create categorical classification bins to teach a model about mass distribution? Could we discretize lighting physics, or material friction, or kinematic constraints? If the field can find a way to tokenize the underlying laws of physics themselves into categorical bins, that methodology might serve as the final architectural bridge between digital visual perception and true generalized physical world models. Something to think about as you design your next training run. That covers the architecture of LingBot-Vision. Thanks for joining us on AI Paper Slop, and we will catch you next time.